Alright, so we've been talking about surface area to volume ratios, and we did a review of it earlier, last week. However, and we did a lab on it as well. I noticed that a couple years ago, they asked a question on the AP exam, and they gave 4 cubes, like the ones I have here, A, B, C, D. And they could have also done it with circles, with spheres, the same way. They said that pretend like these were 4 cells. And they asked which one of the 4, A, B, C, or D, would have the best surface area to volume ratio. And I noticed that a lot of people, because I used the question on a test myself, sat there for 5 minutes and calculated the surface area to volume ratio for all 4 of the cubes. That is completely unnecessary. Remember, and this is actually a test question that you will be asked on Monday, if a shape gets bigger, if I'm just talking about just a cube like this, and it gets bigger and bigger and bigger. As a shape gets bigger, the surface area is going to go up, and the volume is also going to go up. In other words, the amount of surface to cover it is going to increase, and the amount contained inside of it is also going to increase. However, the rule is that volume increases faster than surface area. In fact, volume increases by the 3rd power, and surface area only increases by the square. So, bottom line is, if all your shapes were the exact same size, and you were asked, not the same size, the same shape, I should say, and you were asked which one has the best surface area to volume ratio, the winner every time is going to be the smallest one. Because when I go from a 1 centimeter radius to a 2 centimeter radius, the volume is going to go up, and the surface area is going to go up too. But the volume is going to go up more than the surface area. So the surface area to volume ratio is going to get progressively smaller and smaller and smaller. So you don't have to calculate anything if it's the same shape. Pick the smallest one. That's going to have the best ratio. In fact, in the lab, you may recall, I had where you had the length of a side as your x-axis, and I had you calculate the surface area to volume ratio, and that was your y-axis. If you did that correctly, it looked like this. As the length of a side increased, the surface area to volume ratio decreased, meaning it would take longer and longer and longer for something to reach the center. If we were to drop all 4 of these cubes into vinegar, D would take the longest for stuff to get to the middle. A would take the shortest amount of time for stuff to get to the middle, because it has the best surface area to volume ratio. Okay, so that's if you were given the same shape. So why did we learn all those formulas? The reason we learned all those formulas is because they may not give you 3 of the same shape. So on your short answer Monday, you're going to be given 2 shapes. We're going to do a practice with all 3. You're going to be given 2 of these 3. So you're going to be given a cube and a rectangle and a sphere. You will have to calculate for me, there'll be a little table to fill out, the surface area, the volume, and then the ratio of the surface area to the volume. You want to divide surface area divided by volume to get a single number. Whichever one is the biggest number, that's your best ratio. That's going to be the most efficient cell. So you will be provided with the formula sheet, which you see. I left some on the tables. I have some more. I did notice just today that the surface area formula on the newer formula sheet is different for the cube than on the older formula sheet. It's not that it doesn't change your math, but the way they wrote it is different. So on the formula sheet you have, it probably says 6 times A, which is 6 times the area of one side. The newer version of the formula sheet has this, 6 times one side squared, which is the same answer. It's the area of a side is going to be the length times the width, or the side squared. But I just noticed that it was written differently on the newer sheet. So the one you get Monday, that's actually the formula that you'll see there. All right, so I'm going to give you a couple of minutes. I want you to calculate the surface area volume and the ratio for these 3, and then put them in order from the most efficient cell to the least efficient cell. And we're going to go over it together and make sure everybody's doing it right. And that's what we're going to do. And then we're going to go. All right, so for the cube, surface area, like I said, the formula you're going to see is going to be 6 times the side squared. That's what the formula sheet will have, the one you're going to have. So that's basically 6 times 0.75 times 0.75. And I rounded it to the hundredths. It's not going to change things a whole lot depending where you round. Your units for this, centimeters squared. Volume is length times width times height. Since the length, the width, and the height are the same, it's basically one side to the third, or 0.75 times 0.75 times 0.75, which is going to give you 0.42, and this is centimeters to the third. To get your ratio, you literally are dividing this out. 3.38 over 0.42. You don't need units for your ratio, but your final ratio here rounds to 8. So that is your ratio for your cube. All right. Next, rectangular solid. So rectangular solid is the one, in my opinion, people have messed up the most on the lab. The reason why is because the formula they give you on the formula sheet is really ambiguous. It's the sum of the surface area of every side. I mentioned last time we discussed this, I recommend doing this. 2 times length times width plus length times height plus width times height. To which I had somebody say, well, how do I know which one's the length and the width and the height? It doesn't matter. The bottom line is you need to multiply this number by this number by this number, and then these two numbers by each other, and add that together and multiply by 2. So in essence, it's going to be this. 2 times 0.5 times 1.5 plus 0.5 times 2.0, oops, 2.0, plus 1.5 times 2.0, and then multiply that by 2. If you did it correctly, you should get 9.5. For the volume's easy. It's just length times width times height, so that's just going to be 0.5 times 1.5 times 2.0. That comes out to 1.5. Again, centimeters cubed on that. Divide it out, 9.5 over 1.5. And you're going to get a ratio of about 6.3. For our last one. What? Oh, that's fine. Yeah, I just rounded it. It's fine. Same thing. You would be counted correct. All right, for the sphere, you do not need to work out pi because pi is going to cancel when you divide. So your surface area is 4 pi r squared. That's going to be 4 pi times 0.25 squared. When you work all that out, people thought it was really weird that you get 0.25 back again, but that is what you get. Pi centimeters squared. For your volume, it's 4/3 pi r to the third, 0.25 to the third. For this one, you get 0.021, or if you just put 0.02, that's fine. Pi centimeters to the third. Yeah, you can round it. It doesn't matter to me where you round. Remember, on the AP Bio exam, they're going to tell you to round to the nearest blah, 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 blah. So you do not have to worry about sig figs or try to guess where they want you to round. When you divide these out, the pi's will cancel, and your ratio will end up being 12. Always, I want surface area on the top and volume on the bottom every time. So now if we had to rank these cells in order, which cell's the best? The sphere is the best. So this is number 1. Because it has the biggest surface area to volume ratio. The more surface area per unit volume, the faster stuff would get into the middle of that cell. If you put these 3 in gelatin like we did in the lab last week, the sphere would be first. The cube would be second, and the rectangle would have lagged behind. It would have been third. The more exposed surface you have compared to the volume, excuse me, the faster stuff can get to the middle. Last quick comment, and then we're going to move on to metrics. I did mention to you that there are actually shortcuts for the ratio for the cube and the sphere. So if you can remember them, you could at least double check your work using the shortcut. So the shortcut for a cube, if you do 6, oh, I didn't mean to do that. If you do 6 over the length of one side, that is a shortcut that will give you the ratio. If you do 6 over the length of one side, you will get 8. And for the sphere, there's also a shortcut. If you do 3 over the radius, that will actually give you 12. You'll get, it works every time. You can't just solve the problem that way because I am asking you for the surface area and the volume, so I want to see that you can get the individual numbers. But it's a good way if you can remember the shortcut to double check yourself. Because if you do the shortcut, you get a completely different answer. You're going to know that either your surface area is wrong or your volume's wrong. Something's wrong. Yeah, so for the cube, it's 6 over the length of one side. And for the sphere, it's 3 over the radius. And there is no shortcut for the rectangular one. That would get you the ratio straight away. So if all you had to do was compare ratios and you weren't actually asked to calculate the surface area and the volume, you could technically get away with doing that. This one is always 3 over the radius, and this is always 6 over the length of the side. It's just combining the two formulas. All right. The other thing we're going to do is review really quick the metric stuff. So let me go to the next slide. If anybody still needs this, I'll come back to it at the end. All right, metrics. The formula sheet does not give you this. It gives you only what, like that kilo means, 10 to the third, etc. So my recommendation to you is that you just memorize the cutesy little thing I taught you. King Henry died basically drinking chocolate milk under 9 palms, even though that's not really a U, it's a Greek mu, and do you remember what you have to add over here at this end? 3's. That this is actually a 3 decimal place jump, a 3 decimal place jump, and a 3 decimal place jump. I would recommend that immediately when you get your short answer, you just write that across the top. Then you'll never make a mistake. It's just a matter of just jumping back and forth with your decimals. So from P to N, 3. Correct. So to go from P to N, you'd go to the left 3. To go from micro to milli, you'd go to the left 3. Also, notice this is not milli. I guarantee you one of the problems I give you, I will have M by itself. M is a base unit. That's meter. Millimeter would be this one. All right, so try these, and then we're going to go over them. Okay, so using this little thing, like I said, you won't make any errors. You're going for the first one from micrometers to meters. Micro is here. You're going to count your jumps. 3, 4, 5. You're going 6 to the left. So that's 1, 2, 3, 4, 5, 6. It's 0.00025. Or you could put it into scientific notation. I did have a lab group that put stuff in scientific notation, and every single one of their scientific notations had the wrong exponent. So this should be -4. Just commenting on that, not +4. This second one, millimeters to nanometers. So milli is here, nano is here. It's going to be 6 to the right. So 1, 2, 3, 4. You're adding 2 zeros. It's going to be 3,500 nanometers. Again, you could put it in scientific notation if you would like. 3.5 times 10 to the third. The last one. You will for sure be given something that's in scientific notation to see that you know how to do one that's written that way. Picometers to kilometers. If we count our jumps, it's going to be 3, 6, 9, 10, 11, 12, 13, 14, 15. Since we're going 15 to the left, I'm making it negative. If I was going to the right, I'd make it positive, and all you have to do is add your two exponents together. So this is already -19. I'm going to add to it an additional -15. This is going to be 3.0 times 10 to the -34 kilometers. Again, if you were going to the right, then this exponent would be positive, and you'd add a positive to whatever the original one was. Okay? So that's it. That's how you do these.